16.
Okay, great. Let me make a quick announcement before I start. So there will be a group photo after the session. So don't run off after the session. It'll just take like 5 minutes and we'll meet in front of the waterfall in the lobby. So that'll be our group photo. Okay, so this work I'm going to talk about today is done in collaboration with Pablo Zubko at UCL. And I'm really not going to be showing so much experimental results. I mean, that's the long-term goal, but he's grown some nice films, but we don't have actual measurements of properties yet. So I won't be talking about the experimental results today, but I will talk about some things that he's definitely influenced a lot in terms of understanding what's going on in this system. So this is a session on Hafnia, I guess, and for me, this is all new for me and much more complicated than perovskites and probably most other things that I've worked on. And everything I'm going to present that's new is provisional, but a lot of what I'm going to present is not new. It's just going to be kind of a review of something about this very interesting system. Now, I didn't even remember this myself. Hello? This works. Okay, well, I guess it's not working. Okay, nothing's working. Okay, there we go. So Hafnia is a very important material that's in nanoelectronics. It's used as a gate material in the dielectric, and it's compatible with silicon. So is zirconia, except zirconia reacts with silicon to make zircon, so it's not really ideal, whereas Hafnia tends not to. And recently, by recently I mean in the last decade, it's been discovered to be ferroelectric, which was rather surprising. It's not ferroelectric in bulk, it's ferroelectric in nanosystems, but it's not very well understood. And the properties are very dependent on crystallite size, doping, epitaxy, and really it's not worked out experimentally or theoretically yet. So it's really quite an interesting area. It's not, in the experiments, it's also not very reproducible. So there's a lot of questions about what's going on in the system, and I'll show some of that in this short talk. Most ferroelectrics lose their performance as ferroelectrics in the nano regime, and that's another reason that this is such an important material, because it seems to work better in nano form than it does in bulk. In bulk, it's not ferroelectric at all. Now, actually, I've forgotten more about zirconia and Hafnia than I ever knew. It was actually one of my first papers, and I didn't even remember this, that my first paper as a postdoc was actually on zirconia. And I looked at these phase transitions of these different phases, not with self-consistent density functional theory, but with a model, a first principles kind of based model that wasn't perfect, but trying to understand the stability of this low symmetry phases. Interestingly, the ground state in these, in both Hafnia and zirconia, is monoclinic with 7 coordinated zirconium, and it's just very strange to begin with. And almost everything about it is strange. And one of the things that I did right back then was try to understand the elasticity of this material, which was a whole other story that I'm not even going to get into today. So in 2011, and maybe there were earlier papers that talked about this as well, but it became clear that there was ferroelectricity in thin films of Hafnia, and they were quite nicely measured properties, but also sometimes it was anti-ferroelectric depending on the composition. And even then, it became clear that there were these different phases, a tetragonal phase and an orthorhombic phases that seemed to be ferroelectric, and it was all very intriguing and very interesting. And as time went on, people have done a lot of interesting both theory and experiment on this. This is a paper Karen spoke about in the first talk this morning, which is really important for understanding. This is in zirconia, for trying to understand the observed anti-ferroelectricity in thin films of zirconia. And in that paper, They also mention the possible behavior in Hafnia as well. And I'm going to show a number of papers that have these kind of diagrams, but for me, the more I see of these, the better. So I'll just keep putting them up from different people's papers. But the key thing, I guess, is that the high temperature, high symmetry phase is fluorite. So instead of thinking about starting from perovskite, like many of us are used to thinking of, we start from the fluorite structure, which is also a very symmetric, nice, simple structure. And it just has many distortions. And you know, we think about the 8-site model in perovskites, and I don't know if anybody has the equivalent understanding in these fluoride-based systems, but I think that that's going to have to come down the line. We're going to have to understand exactly what's going on here. So maybe some of you in the audience do, and maybe we'll leave it here to the talks after mine. But like this work that Karen showed, the energetics are very subtle, so the difference between this polar orthorhombic phase and this nonpolar tetragonal phase is extremely small. So this is the interesting thing. It's true also in the perovskites that the most useful and interesting systems are the hardest ones to do computation and maybe experiments for as well, because they're so sensitive, and the whole reason they're useful is because they're so sensitive, or potentially useful. But that means it's also a challenge for us as theorists anyway, and as experimentalists, to figure out the details of what's going on so that we can control it. Because I would say right now, the situation is that things are not completely reproducible. So I mentioned several times this ground state structure is monoclinic. It has this Deliac structure, P2 sub 1 over C. And you can see already it's kind of hard to grasp what's going on even in this ground state structure. And then the polar structure is nothing like the polar structure that we think of in perovskites, where, for example, the long axis is the polar axis, and here the short axis is actually the polar axis. And if you just look at the picture, it's not so obvious, like why it's polar. I mean, there are displacements of the atoms that contribute to the polarization, but it's not something that just jumps out at you like it does in very tight date or something like that. So some very nice thin films were grown epitaxially in 50-50 Hafnia zirconia, and this just shows some of their films, data, and some of their ferroelectric properties that were measured. And again, it's getting better. People are measuring reasonable polarizations and reasonably reproducible results for a given growth conditions. And there's been some interesting theory done along the way as well. This paper by Batra et al. Again, talks about these different structures, but here they emphasize the importance of this PBCA structure, and then this polar, these different polar ground states. And here they point out very clearly the importance of epitaxial strain on the stability of these different structures. And this is the problem that's really hit all of the theorists over the head, because you would like a nice, simple story that you just epitaxially strain the system and it automatically becomes polar. But in all of the calculations, it always comes out that a nonpolar structure is more stable than the polar one. So even though, here's the monoclinic structure, and then if you put in a compressive strain, this orthorhombic structure becomes more stable, so that's nice. Except the one that's observed experimentally is the black curve. And instead, in theory, one always gets the nonpolar one to come out instead. And, you know, maybe there's something wrong with DFT, but you know, us theorists would like to understand things a little deeper than that. One of the things that people have thrown out as a possibility, I must say I'm not completely taken by this, is the idea that this polar structure is actually stabilized by electric fields, but they're reasonably high electric fields, like 200 megavolts per meter. I mean, it's possible. But anyway, so if you drive it with an electric field, you can make this polar structure stable. And so this is showing monoclinic, the non-polar orthorhombic structure, and then the polar orthorhombic structure is a function of strain and electric field. Anyway, this paper really clarifies a lot of the issues that are present. And it doesn't seem to depend on what flavor of DFT you use. There's no flavor, as far as I know, that stabilizes the polar structure as a ground state under zero field conditions. Now, to make things more complicated, this is an experiment and theory paper that tried to emphasize the importance of a different structure altogether, a rhombohedral phase. And so this R3M phase, turns out, is also competitive. And they did calculations where they showed large polarizations and experiments where they found this phase in their thin film growth. So now you have a whole other story of a very similar films, except that they're rhombohedral instead of orthorhombic. And so it seems like both are possible. I don't think they're saying that the other data were wrong and that they weren't really orthorhombic. So we see that under different conditions, one can form these rhombohedral systems and these are ostensibly under the same conditions. Now there's also the issue of doping. For a long time, zirconia and hafnia have been targets of doping. We know cubic zirconia, for example, you can pick it up in any cheap store as a diamond substitute, and it's just zirconia with like yttrium added. It stabilizes the cubic phase. So we know that you can dope these materials and stabilize different structures. In this study, they tried to understand, they actually emphasized unusually large, but I don't know that I'm completely won over by that. That what they actually found was that no matter what they doped it with, still the nonpolar phases were the most stable. So nobody's really explained, even by doping yet, the stability of the polar phases. But they did show that if you dope it, you can stabilize phases other than the monoclinic phase. So that part is clear. So we know that it's fairly easy to make this orthorhombic phase, or maybe rhombohedral phase, by strain or by doping, but making them polar is still an open question. I wish that Xi Lu was still working with me, because he wrote this beautiful paper, so I'm highlighting that here. This is on the archive. He told me I could put it up here, but it's not published yet. And he did some really amazing work at the Army Research Lab, where he is now, to look not just at the stability of these different phases, but also the pathways between them, the energy pathways between them. And one of the things that he found is that, and the other thing that's very nice, I need to go back and do this properly, is he very carefully and exhaustively figured out the epitaxial relationships of the different orientations of the different phases on surfaces of different types, so that you can actually figure out what's going on. The problem is you're starting out with something that's monoclinic or orthorhombic, and so that means that it matters. You can't just say like 100 or something, because maybe it's the other. You can switch A and B, and it's a different. They're not equivalent. But they have very similar lattice vectors, so you can't just look at the lattice vectors and see which is A, B, or C. Anyway, one of the things that he found that's extremely interesting to me is quite a large barrier between the polar phase of this orthorhombic polar phase and this nonpolar orthorhombic phase. So they look very similar when you look at where the atoms are. This is the nonpolar or antiferroelectric orthorhombic phase, and this is the polar one. And you can see this bit here fits over here. So it's really just a doubled cell. It's like a zone boundary instability that gives you this PBC A structure. But nevertheless, even though it looks like it should be very simple to distort one into the other, at least what he found in this paper is quite a large energy barrier between them. So I'll kind of cut to the chase. I haven't even shown any of my results yet, but I think that once you stabilize or grow these polar structures, they're stable, metastable, and it's really the growth conditions that are most important. So if you can rig things so that the polar phase forms, then you get a ferroelectric. And it's not that it's the most stable phase. It's not that the doping or the strain stabilized the polar phase, but rather that the growth conditions were such that it grew. And then once it grows, you have a polar system that can act ferroelectric. This paper just came out a couple weeks ago, which is very interesting, where they actually were experimentally able to map out the double well in Hafnia transiently. And I just wanted to show it, not because it ties into anything in particular, except that just all of the excitement that's going on in this field. Okay, so I have a couple slides of my results that are completely confusing. Oh, good, it's time to stop. So no, I have a couple minutes here. So I want to try to explain these to some degree. So this is just showing energy versus strain. So these are epitaxially strained calculations with a fixed A and B axes on a surface. And the ground state, as everybody else has found, is monoclinic. And as everybody else has pointed out, under compressive epitaxial strain, you can stabilize this polar orthorhombic structure. The thing that I did that's different than everybody else did is I ignored the nonpolar phase, so it looks like I'm getting the right result. So if you don't worry about the nonpolar phase, you can show that epitaxial strain will stabilize the polar structure. Anyway, but this also shows, though, this rhombohedral phase, and this is one of the things that's very hard for me to get my mind around, is that I actually get slightly different results depending on what structure I start with. It turns out that there seem to be a lot of local minima. I mean, it's not just a random difference. I started with like a different sign of the oxygen displacements relative to the zirconium displacements. And in one case, I got this green curve here for the rhombohedral structure versus strain, the other one, the black one. I mean, they're very similar, but they're different by 10 millivolts per atom. So it is significantly different. I guess you could consider this some measure of error or something, but it also, I think, is something real, that there's different local minima in this structure. Also shown here this is a nonpolar cubic phase, which is interesting because it's piezoelectric, and I don't think people have talked about this, but I find it to be also one of the low energy phases, is this P bar 4-3M structure, which is also a relative of all these and distortion of the fluoride structure. But it's interesting because it's cubic, and so it's not polar, but it doesn't have inversion symmetry, so it's a piezoelectric structure. Let's see, and then I should probably go ahead. And this most complicated set of results, I want to spend a minute talking about this, and I guess this is what I've spent most of my time doing, is trying to calculate the polarization of all of these polar structures and understand them better. And in the process here, found something I think very interesting. So first of all, let me point out that all of these orthorhombic structures have fairly small polarizations. I mean, they're not tiny, but they're like on the order of 0.1 or 0.2 coulombs per meter squared. And the other thing is that many of them have the polarization in the plane. So if you're measuring for thin films, if you're not set up for doing that, you might think you don't have a polar structure, but it's just that the polarization is perpendicular to the direction you're measuring. But the other thing is that in many cases the polarization ends up being oblique. So even if you're measuring the c-axis polarization, you're only going to pick up a part of it. So that's interesting to me as well. So here, this green and blue are different versions of, one of them is with the polarization out of plane, and one's with polarization in plane, and this is again with epitaxial strain. And then this is this rhombohedral phase that Nohita's group talked about. And you can see it has a much higher polarization, but only at very high compressive strain. So whether you could